So why don't we get started? Um, we are in chapter 16, and I believe we did not talk about sentiment analysis, and that's what we're going to start with. But first of all, of course, we got to start reading. And for those of you who have not finished sentiment analysis, please still, continue through that. But we want to read from sentiment analysis to the section right before bidirectional RNNs. Gotham and I had a quick discussion, and he was saying basically right before this should be okay. So that's what we're gonna end right before bidirectional RNN, and that is on a physical book, page 546. Okay, so I'm gonna type it in, and we're gonna spend next 45 minutes reading that. I don't know if it's gonna be enough. If not, we can extend it for another 15 minutes. But
So 534 to 546.
yes.
Okay.
Okay. We will resume the discussion at 10:30 p.m. EST or 7:30 p.m. PST. Talk to you guys later. Okay, time is up. Let's get started with the discussion. Did everyone finish reading, or you want a couple more minutes?
I'll speak up. I'm done.
You're done? Okay. Anyone else? It's fine. All right, so seems like everyone finished. Great, so let's get started. With the discussion from sentiment analysis. Let me start sharing my screen. Okay, sentiment analysis is has always been a fascinating topic for me, particularly, and I worked actually in the startup, specifically focusing on emotion analytics for marketing purposes. So I can speak to some of the use cases that are pretty popular within the different industries. Yeah, but there's a difference between sentiment analysis and something that's called emotion analytics. And when we say that, sentiment analysis typically refers to positive, negative, neutral. However, emotion analytics would typically refer to identifying emotions that the actual emotions in a psychological definition could be love, happiness, sadness, fear, anger, so on and so forth. And uh, if you're interested in emotion analytics, there's or sentiment analysis, there's a pretty good book on this, and it's called, I believe it's called Sentiment Analysis, Bing Liu. Yes, I have this book and I read it. It was pretty good, but it doesn't have code. It's more like kind of an industry kind of survey type of book. It did in the domain knowledge on the topic, and Bing Liu is probably ranked #1 on Google Scholar within the sentiment analysis space. I believe he is he works at one of the universities in Chicago, if I remember correctly. Anyway, and I guess are there any questions up to this point on sentiment analysis? I just give a kind of brief introduction. And obviously, we're going to be using IMDb as a data set for this, and that's sort of just as he said, it's the hello world of NLP or sentiment analysis. So. Okay, so and I'll probably talk about some of the use cases in a little bit. Someone posted something on chat. Okay, great, thank you. So, in TensorFlow already has this data set. So all we had to do was basically just keras.datasets.imdb.load data, and specifying the xtrain, white test, xvalid, white test. Is that Shouldn't that be Y train? Does everyone have Y train? Or anyone?
It should be Y train.
Yeah. I thought, I just noticed this. But do you have the same thing, like Y train, Y test in your notebook?
Yes.
Okay. Because the book, the physical book actually is correct. It has X train and Y train, but somehow the notebook is wrong. So just make a note of that, I guess, because obviously it will create trouble, and I just noticed that. So, train. Okay. Okay. So, and we can kind of look at the training data. It's already indexed for the words. And obviously, we all know what it is, right? I don't think I need to explain what IMDb reviews are. It's basically a bunch of movie reviews. However, each of which is represented as a numpy array of integers, where each integer represents a word, and the word is indexed. So what you're seeing is actually the index of the word within the vocabulary. Okay. And also, when you pre-process the text, you also want to add in special tokens such as padding token, start of sentence token, end of sentence token, things like that. So basically your sentence will be like something like this, with the start of sentence token. And obviously this has been pre-processed by a lot. So he was saying basically, Jerome was saying, obviously in a real project, you got to pre-process the text yourself. And that's actually where a lot of the difficulties of NLP come in. It sometimes the text data could be pretty messy, and there are different ways to pre-process text and pipeline it. So any questions so far? And this is just downloading the data from TensorFlow datasets as TFDS and splitting the train test right here. Printing out the reviews with the labels right here. And he wrote the preprocess function right here. And note that he truncated the reviews to first 300 characters. And he explained that as basically, hey, you don't need all the text to be able to tell that it's actually a positive review or a negative review. And 300 characters might just be enough when it comes to performance. So. Yeah, I think this part is pretty straightforward, but what was interesting was just basically he wanted to keep only the first 300 characters. And but I guess, when it comes to real projects, you want to test this number, right? So and he also padded each of the review with padding token pad so that they all have the same length. And then you construct your library and basically using a counter. So he didn't, well, since it's a library, he just used a counter and count the frequency as well. And as you can see, basically now all the words are tokenized. And also you have the frequency on the side as well. And we're not doing, I believe in this case, we're not doing subwords. We're just splitting the words by spaces. Just the color a little bit. And also he made a decision that he only wants to keep the 10,000 most common words. That's also a decision that sometimes you want to make if you have a pretty large data set and you don't think limiting this will affect your performance. And or sometimes you just want your model have very low latency and you want really fast inference, then you want to limit some of these parameters.
So just a quick query.
Mm-hmm.
This number of OOV buckets have their space in VRAM if we are training on a GPU, right? Or will it be on the RAM and each time a new batch is being run, that table will lookup will be performed across that uh, bus, and there will be some sort of, how do I say it, transfer of information from RAM to VRAM, or it will all be combined and placed into that GPU's memory?
I'm not sure that I know the answer to that question. Anyone has a clue or answer that how does OOV bucket interact with memory?
I think it must work by hashing in some way of, it hashes the word and words with the same and words with this, and then they do something with the hash number. They take its modulo or something, and then words with the same modulo go into the same bucket. So like you create some large number and then take modulo, and then take that number modulo 1,000 because there's 1,000 buckets. And then so each number goes into the bucket corresponding, or each word, new unseen word, you generate this large number and then you take its modulo, and then it goes into that word goes into whatever bucket corresponds to its modulo.
And I had some questions on this as well, because I was like, what if I have more than 1,000 words that are not within the
Right. That's how the modulo thing works. That's how the modulo thing works, right? Every word you create you create this large number starting with that word, and then you take the modulo of that number, modulo 1,000, right? So
Uh-huh.
the result can only be numbers 1 through 1,000. So there could be lots of different words that have the same, that have modulo 2, and all those words would go in bucket number 2. And all the words with modulo 67 go in bucket 67. So no matter how many words, unseen words you have, there's only 1,000 buckets to contain them, and that's controlled by the modulo. You just take a large number modulo 1,000, and that decides which bucket to send that word to.
So 1,000 pretty much would include everything. How does this modular work?
Well, okay. Suppose you have, well, okay. Suppose you have the number 21, right? And you take the number modulo 3, then or modulo 2, let's say. 21 modulo 2 is the remainder, right? It's 11, right? Sorry, modulo 2 is 1, right? If you take 21
Yeah.
modulo
Mhm.
2, that result is 1, right?
Mhm.
So so now imagine taking a number modulo 1,000, a large number, and then take it modulo 1,000. There's only, it can only be, the result can only be a number between 1 and 1,000. Or what is it? 0 and 999, right? So there's only 1,000 possibilities. So no matter how many new words you send into this hash, into this thing, it will assign those words to one out of the 1,000 buckets. You can't, there can't be too many words, because it could be that a lot of different words will be sent to the same bucket, but at least at least you'll be able to handle new words.
Yeah. And as we are seeing here, basically, this movie was fantastic. And obviously, this movie these 3 words were able to be looked up in the vocabulary. However, this fantastic very obviously does not spell, in the correct English grammar, as people just want to emphasize that they're really excited and they add a bunch of A's.
Mhm.
But so that gets assigned to one of the OOV buckets, and it's probably 53, I guess.
Yeah.
Yeah.
One more query here. So the words that are assigned to the OV buckets, are they or do they have some sort of a priority, like the number of counts? Uh, uh, those words that have the highest number of counts will be assigned first, and those with the lowest might be left out if there isn't any space on those default bucket sizes. Is
Well,
that
you can't run out of space, right? Because every word will get sent to exactly one of the 1,000 buckets. No matter how many weird looking words you have, this method will handle it just by figuring out some bucket to send the word to. And in this scheme, you could have more than one different weird looking word get sent to the same bucket, because it has the same, modulo 1,000, it's the same number. And that's just the way it works. Yeah, so it's not a unique way of assigning words to buckets, but at least it gets around the problem of what to do about new words that you haven't seen before.
But there should be some sort of priority too, based on if you think about the number of words that will be used, that have that have the highest frequency versus the lowest
Uh-huh.
one. So they should be assigned first, and because the hash is being calculated, and for every new bucket that has to be created, it will take a bit of a memory. and that creation will have some sort of a memory as well as time complexity associated with it. So I was just thinking from practitioners or the implementation perspective, it makes much more sense to have some sort of a sorting be applied on the pre-processing of those uh, those counts of words and assign them according to some sort of uh, uh, efficient use case.
So in other words, you're saying you populate the lower buckets first, uh, or I don't know. I guess yeah. Hmm. But I guess it's impossible to say beforehand which bucket is going to get the most words.
Yeah.
I mean, if you care about those words, you can just increase your vocab size, right? If you're at 10,000, you can just bump that size up. And then you'll still be maintaining the priority of most frequently or the most common words. And then you'll still be having embeddings set for them. And there's going to be no collision in that instance. The moment you're kind of jumping into this overview, it's kind of like a compromise between that the word is really important versus kind of you are letting the collision to happen, right? So more than one word
Yeah.
will probably get mapped into a bucket.
Yeah.
Um,
And
But I guess what saves you is that the weird words are not likely to be
that
frequent.
right.
Yeah.
yeah, and seems like each bucket is has its own embedding, right? So meaning,
Right.
so if you have a bunch of words in one bucket, then these bunch of words will share one embedding.
Yeah.
Seems like to be the case.
Yeah.
Yeah.
And if you happen to see any of those words again, you will be happen to use the same embedding, right? It's not like having one unknown token where everything unknown is getting mapped to that. Here, at least, let's say if they have 10 words in one bucket, which has one particular embedding, if you see any of those 10 words again, you will end up using that same embedding.
Yeah.
Okay. So he also wrote a quick encode words function. And basically it's just table.lookup x batch and with y batch. And then you just twinset.map encode words prefetch one. Again, prefetching is just fetching the next element while the current element is being processed. And in this case, we just want to fetch the next element. And now if you loop through that twinset and you print out the X batch with Y batch, it will look like this. That's the X batch, that's the Y batch. And since the batch size is 32, that's basically the target label. 0, I believe, is positive. 1 is 1 positive or 0 positive? Forgot. Did he mention anything like that? Okay. Let's take a look at that. 0 is negative. Okay. 0 is negative, 1 is positive. And the training data with the batch looks like this, with the shape of 32 and 60. That's the column size. And if you look at a lot of these zeros, that means they've been padded. Okay. And also, then basically we can just architect the model, and with one embedding layer, 2 GRU layer, and 1 dense layer in the end. We're using activation of sigmoids in the end because it's only positive or negative. It's binary classification. And we specify the loss as binary cross entropy. Optimizer, atom, metrics accuracy, and GRU units of 128. So I did look it up, GRU, and what does units mean. I think Joseph was probably right. Basically, it's the dimensionality of the output space. And so if we look at the GRU's architecture back in chapter 15, right here. So the outputs, I suspect it's either the HT or I think YT could be equal to HT. I believe it's the HT's dimensionality. That's the that's what 128 is. So I'm glad we cleared that up. So great. Any questions on this? And we're able to reach accuracy of 96% with just 5 epochs. It was fairly quick, 24 seconds. And again, this embedding is, I believe it's 11,000. And it's probably 128 of the column size as embedding size. Yes, embedding size. That should be the, because you got 10,000 vocabulary, 1,000 OV buckets, and each row is one word or one bucket. Then and also each word should have embedding size of 128, so 128 columns. Okay, any questions on this?
Those 128 will be the number of cells in the GRU layer. So, and those embeddings will be, yeah, 10,100. Yeah, yeah. So, uh, I was just confused as to the visual representation of it, because those embeddings will output those layers into the as a input to the GRUs. So those hidden, I think so, those hidden context H of T will be uh, uh, flown from the bottom to the top. If we look at this sequential deep neural network of 3 layers. So, is my interpretation right? Just wanted to
Um,
clarify.
could you clarify what your interpretation was?
Yeah, so my interpretation was with respect to those embeddings and those
Mhm.
hidden uh, weights, those H of T,
Mhm.
those that has to be transferred. So those each and every embedding will have a how do I say it, impact into the input to the CT. If we look at those layers. Uh, so
Mhm.
how, I was just curious, how will the embeddings have a input to the GRUs? Will it be via the straight? Uh, uh, Let me try to annotate it. We have this. This will be 128 layers, if I'm not mistaken. And this will be edge, which will be flowing. And the embeddings, if I draw it here, these will be the embeddings. And these are the cells. So I was just thinking as an input. So X, will it be flowing it this way? I mean, and then there is another layer of GRUs. So this will be the first with 128 and those Boolean flag of retain sequences is equals to true. Return sequences is equals to true. And this will be the second which inputs if we unroll this. I was just trying to clarify what will be the correct visual representation or intuitively what uh, if this diagram is correct in the sense of those deep neural networks of 3 or 4 layers, and then in the end there will be an dense layer here, which is sigmoid activation. So this will input all of this here. In the end, we will have a single, I think so, here, yeah. Just trying to get a,
Yeah, I believe that's the case. And anyone else has any thoughts? I believe that's how it works.
there will be maybe slight uh, mistakes or some uh, representations with respect to the flow of how do I say it, those return sequences or uh, how do those GRUs map to the last dense layer? Yeah, but all in all, I think so. This is the way to go.
I think on the last layer, you don't have the second GRU that you have, return sequence is not equal to true, right? So it will probably use just the output from the last one, not the outputs from each and every
Yeah,
one, and
I
then
agree.
pass it through the dense.
Mm-hmm.
I'm not sure, at least that's
Yeah,
what it looks
yeah,
like.
Yeah.
The difference from the code, right? Yeah.
Mm-hmm. I agree.
yes, yes, it makes sense. Yeah.
Yeah.
And in the first one, with is this right too? The first embedding, will each of those spaces and the size will have its own, I think so, copy. So in the memory, there will be embedding space here,
Mm-hmm.
which has one this guy. And will this be a simply copy of
That
this?
embedding matrix should be 11,000 rows by 128 columns, right?
Mm-hmm. Yeah.
Mhm.
So let's say you're pulling out 5 words. The first
Mhm.
word you will look up in that embedding matrix, and you will just get out a vector which will be 1 by 128. So just one row of that. So the dark green
Oh,
X that you've drawn, that should just be a vector 1 by 128.
oh, oh, okay, cool. That helps.
I think that's
to
what makes
make-
sense to me, like, because your embedding is kind of, you're picking one word, you're picking that representation, and then you're passing that.
Hmm.
So just to make this complete. This X
Except
will
you're,
be
I think except you're batching it, right?
Yeah, true. There's a batch. Yeah, this is
Yeah.
assuming that you have only one batch.
And so it should be probably 32 by 128. Then for 60 tokens, then you're doing 60 steps. I believe that's what it is.
okay.
Yeah, I'm not I'm confused myself with like 128 versus 60 steps. I always get confused with that. So I don't know which one gets repeated across. This 128, I think, is just the output, right? So it's not like there are 1 in 128 repetitions. I don't know. Someone, can you kind of confirm that? Gautam was talking about this last time. I forgot what it was already.
So the question is,
Where did you
what's
come
the-
up with 60, Wenchang? Actually, let's start from that. I missed that.
I was just looking at this.
And that is,
That's the X batch. X
okay,
batch,
right. Okay.
one
Sorry.
batch
Yeah,
size. Yeah, 32
makes
by
sense.
60.
Okay.
Yeah. Can anyone confirm this? We're talking about if is each time step one token or one word in this case.
Yeah, like where does that 60 sit and where is that 128 from the GRU's unit sit? The 128 from the embedding size, I think, kind of makes sense.
128 goes to here, but also I think the 128 here goes back to what I was saying. Basically, it's the dimensionality of the output space.
Right. So
And
in Mayank's diagram, where would that sit?
I believe it's the hidden. It's this. It's what's passed through this.
Okay.
And also, yeah. Go ahead.
Yeah. So 128 will be the number of cells here. So this is 1, 2, 3, 4.
No,
So
I don't think so. It's the dimensionality of the output space, not 128 steps.
So we are thinking more about in the terms of spatial. So if we draw it like this, so this will be like this.
So rather, Mayank, I think your 1, 2, 3, that will end at 60, right? Because of the sequence, right, Wenchang, or someone else,
Yeah.
please correct me. Okay.
Yeah, at least that's what I think. Yeah.
Okay.
So still, where does this 128 come into picture then? This GRU's 128.
I believe it's the this is going back to the equation.
Oh, so it's like h of t and y of t is a one
Yeah,
by 128 dimensional vector. Okay.
Exactly.
That
Yes.
makes sense.
Yes.
Okay.
So
Okay.
and this gets passed through, right? This is
Right.
one GRU cell, and it gets passed through every single step. And this is the hidden state, right? And we're talking about hidden state unit size of 128. And it's also what's referring to here, dimensionality of output space. Yeah.
Cool.
Okay.
Let's clear out the diagram.
Okay, anyone else wants to say anything before we proceed forward with masking? There's something that's called manual masking. Look at the book. Basically, I mean, masking, what masking is basically instead of, I think he said it right here. Gonna go back. Well, like you don't have to basically let the model learn what a padding token is, and it should be ignored. Why don't you just tell it, right? And so set it as a parameter, and just simply adding like mask 0 equals to true when creating the embedding layer. So basically, when we have it here, it's just mask equals to mask, and you have a mask as here. Well, that's the manual way of doing it, I guess. But so he created something that's called a mask tensor, equal to k dot not equal inputs 0. It's a Boolean tensor with the same shape as the inputs, and it's equal to false if it's padded with 0, or true if otherwise. So if it does have a word at that index, then it will be true. Basically adding a mask layer on top of it, which is this. Okay, and you pass through that into this. Okay. And comparing the accuracy, I mean, there's not much difference. But also he said there's warning, as we kind of said at the beginning. LSTM and GRU layers have an optimized implementation for GPUs based on NVIDIA's QDNN library. However, implementation does not support masking. If your model uses a mask, then these layers will fall back to the much slower default implementation. So, so when you run through this notebook, if you haven't noticed, or if you haven't done so, make sure you basically, well, if you want to have a faster training process, just make sure you kind of comment out the recurrence dropouts. And also in this case, masking as well. It does not support masking. But for this data set, it's still relatively fast. It's just, yeah.
It doesn't throw that a warning. So that's what's strange. When you use manual masking, it doesn't give you that warning that you're getting the fallback version of the network. So I don't understand that.
Yeah, I didn't get a warning either. Interesting. The other thing I think he mentioned is the transfer learning part of sentiment analysis. I believe if you, for those of you who have gone through FastAI, that's what actually Jeremy did with sentiment analysis. He used language model transfer learning on Wikitext 103, and used the encoding part of the model, and then have that as the embedding for his sentiment analysis. It was quite interesting, and he was able to reach a higher accuracy results. Anyone recall that from the NLP lecture? I thought that was amazing, because I never would even think of using encoding part of the encoder decoder network as embedding. That supposedly you have learned from a language model, and then use that as the semantic meaning of words for sentiment analysis.
Like
thought
three
that was
parts
brilliant.
to that, right? Like he
Yeah,
uses
3
the
parts.
wiki 101.
Mhm.
I mean 103,
103,
and IMDb comes with 10,000 data points. I mean 100,000 data points, right? 50,000 are labeled, 50,000 are unlabeled.
Yeah.
See, so he fine tunes the wiki model with the 100,000 data points reviews, so that the language model gets updated, and then he uses those embeddings.
Yeah. But even, you know, I'm surprised that we're able to reach 96% without a pre-trained embeddings here, and we did not use any pre-trained embeddings. We're still able to get to 96%, so that's pretty cool as well. Cool. So I kind of dropped down a couple notes on like use cases, because I've was in the space, so it's always good to touch upon use cases because a lot of fields are emerging with AI and ML. I think it's always good to talk about use cases, and some of the use cases would include aspects associated with sentiment slash emotions. I think we were in the Kaggle NLP project or group that we were tackling a Kaggle data set that was specifically for this task. Basically, you want to extract the words that are associated with, or the words that identify the emotions, and um, so that's that. But I guess there's a difference between messaging or lexicons associated with sentiment, emotions, and also the aspects. The aspects are more like, you know, what are you expressing your emotions towards, right? It could be like, hey, I just watched a very exciting football game. Then in this case, it will be a football game. That's the aspect. And the lexicon that I used was exciting. And now this is more for marketing, because a lot of times you want to speak your audience's language. So, you know, if your audience is using the word exciting, then you might want to use exciting instead of saying happy, or, you know, um, um, what's the other word that I could express excitement? Um, or it was a fantastic football game. You know, basically you want to extract the words that people actually use to express their sentiments slash emotions, and also you want to know what they're expressing their emotions towards. It's really the case that, you know, in the industry, that you would just stop at, you know, predicting this reviews sentiment. That's not as useful. The other thing is you might want to score them. So let's say you have uh, basically, use refresh this. Okay, so let's say you have one product, second product, and 3 products, and each product has, you know, could be like 500 reviews, 300 reviews, and I don't know, 400 reviews. And you, let's say you predict use a sentiment analysis or sentiment prediction model, but also calculate the score of that emotion or sentiment. So it could be maybe, I don't know, 75% positive and 90% positive, 80% positive. Now, okay, so while this doesn't look very good because it's 75%, I want to dig into, hey, let's separate out the 1-star or 2-star or the, very negative reviews. And let's get the, so it goes back to the aspects. Let's get back to the aspects. What are the aspects that are associated with this particular product? Does that make sense? Okay, some of the difficulties: multiple emotions expressed at the same time are hard to detect. So this goes into the concept of sometimes, a person could be expressing happy and sad at the same time. Even sometimes it could be like I don't know, angry and sad at the same time, and that could be harder to detect. And emotions expressed through tons of language also hard to tone of the language also hard to detect. Basically, sometimes we say one word, one sentence, but when we read it, it could be to mean a different thing emotionally. And secondary emotions are hard to detect sometimes, even for humans. And when I was doing the startup, we had to a lot of times dig into the secondary emotions, because that's where the richness of the data comes in. This has huge gaps, right? Between anger and surprise, there's huge gap of information. So you want to have a more continuous spectrum of emotions, but of course that adds a lot of complexity to that, and it's almost impossible to classify these many emotions anymore. But primary emotions include 6, like 1, 2, 5, 4, 5, 3, 4, 5, 6. Fear, sadness, anger, surprise, joy, love. Secondary emotions would include a bunch of them listed here under each category. Anyway, without digging into further too much into that, that's kind of what I got to know in terms of some of the use cases and difficulties when I was dealing with sentiment analysis and motion analytics. So, any questions? Cool. So let's march further on this. We're using pre-trained embeddings. I think we were just talking about transfer learning, and he is using basically one of the models here, NNLM in English dimension 50. Let's take a look at what that is. It's token-based text embedding trained on English Google News with 7 billion corpus. Really huge data sets. Details. This module takes a batch of sentences in the 1D tensor strings as inputs. And also it's version 1. I think he highlighted that. It's always good to know what versions of models that you're working on. And it's also a good production practice to version your models. And beyond that, also version your data sets. And I'm sure many people in the room can speak to that in terms of production practices. You always want to know which caused what. If this model didn't work, or this version of the model did something like that, something unexpected, and you want to investigate further. So you want to go back to the data set that trained this version of the model. So you want that exact version of the data as well, and you dig into it further. And sometimes people would even version or would even label the features and assign features to people as well. So versioning it is very important to help you to debug and monitor the models. Okay. And basically you're just loading this model from this particular URL. And with a dense layer of 128 units and a final dense layer, a final output layer, or with the 1 unit activation sigmoids. And with that pre-trained embedding, instead of training your own, somehow I think the accuracy, did anyone get a lower accuracy? You know why that is?
Yeah, I got a lower accuracy too. Although the initial result after the first epoch was higher, but the end result was lower.
Any reasons why anyone figured out? I was curious about that.
I don't know, but I'm wondering if so what we're doing here is we're downloading this thing with pre-trained weights. And are we just using these weights out of the box and not letting it learn new weights? Or maybe there's a way to turn it on to say, okay, now start with those values, but learn new weights.
Yeah.
I'm not sure how this is working.
Yeah.
Maybe we can instead of using the pre-trained embeddings, we can use our own. There is a library, TensorFlow Text, which gives us an uh, uh, interface to train our own embeddings based on the popular algorithms with respect to word space or n-grams, sliding window, and all. So maybe that will also have some sort of uh, prediction threshold impact to the whole process, because those embeddings will have some sort of different clusters if we have our own uh, training that we do, those pre-training, and that will also result in the change of uh, those numbers depending upon the online. Suppose we have that it dynamically takes in some new words. If I take an example of a retail, suppose, in which new products are being added weekly, and our production model has to be productionized embedding model has to cope up with those new products that are being added to the embeddings. So maybe a weekly batch will run with respect to those new uh, uh, words and those new products, and those will be added, and those that will come into the pipeline, and that will be deployed with respect to uh, the requests that has to be provided to our customers. So just a pipeline example. So I was thinking more in terms of productionizing it and how dynamically can we change it, because only this embedding component will be different. Rest of our uh, uh, pipeline will be the same.
The embedding size is different here, right? When we were using 128, we're using 50 now.
50, yeah.
And the
Yeah.
other thing which kind of
That could
looks
be,
right,
yeah.
and the other thing that kind of looks interesting, I don't know how sentence encodings usually work, but here it seems like it takes and generates a vector for each word and then takes an average of those.
Embeds each word using embedding matrix that was pre-trained. So it parses a string, splitting words on spaces.
Right.
Yeah.
And then it computes the mean of all the word embeddings that are there in that sentence.
Yeah, the main of all the word embeddings.
Right.
Yeah, and
so
the
that is
result
something
is,
which is again going to be different from what we were previously doing, right?
Mm-hmm.
So here, like the order of the words don't look like they're important, right? Because you can have the order in any way and the means would still turn out to be the same.
Mm-hmm.
So
Yeah.
I'm guessing those.
So instead of using the actual word embeddings, we're using sentence embeddings.
Right.
Yeah.
Yeah, and I don't think that makes so much of a difference, but I don't know how OOV is handled here, right? There we were having that issue with 1,000 buckets.
Mm-hmm. Mm-hmm. Yeah.
You can also go and get different embeddings. I tried the dimension 128 embedding, and it was better, but still not. It didn't get to 95%. It started out at 75%, and then it ended up at 83%. But that's not as good as the previous. That's not as good
Right.
as
So
the
if I
main
were to
one.
guess, it's kind of because that mean factor is coming into play for the whole
Yeah,
sentence.
it's squishing out there, it's sort of smoothing out the information.
Yeah.
The other things to try would be to, there are better sentence embeddings now,
Correct,
like
yeah.
as Gautam has pointed out, is in the Kaggle competition, there is this universal sentence encoding, which doesn't do just the averaging, it does much more complex transformer-based approaches. And then there is SBERT, which is BERT applied to sentences. And again, both of those generate sentence encoding. So you could just drop in, replace USE and SBERT and see what the score is. But even in similar tasks, like what we're doing with the NLP Quora questions, it seems you will get a better score, or at least you often, unless you do ridiculous things, you do get better scores when you use word level embeddings or sub word level embeddings to then build the network and use it rather than just relying on sentence level embeddings.
Yeah. If I remember correctly, there was a fine-tuning process that Fast AI did, Jeremy Howard did. That's how he reached basically higher accuracy with sentiment analysis. And I don't think this fine-tuning process is happening here.
Yeah, that's why I was saying, I was wondering if there's a way to, there's a switch that you can, in other words, it's just taking the pre-trained embeddings and using them without learning, without trying to improve on them. And I don't know if there's a switch that you can set that would say, okay, now take those as the starting values and improve on them.
Isn't the next section talking about that, where he talks about something you can set true? Where was that? I thought I read that. Was I?
Next section is encoder decoder.
Never mind. I thought. Oh no, just above the warning is in there by default. Hub.keras layer is not trainable, but you can set trainable is equal to true when creating it.
Which one?
I'm on the Kindle page 541 about the warning.
Oh, the warning. Make sure.
So right above that, by default, hub.keras layer is not trainable, but you can set trainable is equal to true when creating it.
Ah, okay. So that you can fine tune trainable equals to true.
But I don't see that in the example, so I don't know where exactly. Oh, I guess in Keras. Okay, hub.keras layer is it.
So why don't we try
there.
this? Trainable equals to true. So why don't we just cool. We'll let this run. Thank you. That was a good call. Equals true to fine tune the process. So I wanted to see obviously this one. Believe. Yes. So see, fit one cycle. It was there unfreeze. Yes, unfreeze. So there's always a freeze and unfreeze process, and that was the switch, Joseph, in at least for Fast AI. You always like freeze to this, and you unfreeze it, and then you train more, basically. You know, you're to be exact, you're fine-tuning the last two layers, the last three layers weights to update further for your local or for your, you know, smaller data sets. That was the Fast AI way. So, all right. Oh, there you go.
Oh,
Hey.
so that was it.
Yeah. 98.92. Hey. I don't know why he didn't do that in the first place, but
Yeah.
why do we need a 75% accuracy model? All right, so I think let's quickly, well, I think it's getting a little late and I don't want to rush through the encoder decoder. That is a big part of the discussion, even though he only covered it for 4 pages. And so I don't want to rush through this. So we can probably just cover this the next time. And it will be either Gotham or me covering the chapter, depending on how busy he is. So, so we will, any questions for the sections that we have covered so far? Everyone good? Cool. All right. Well, I just want to thank everyone for joining the session. I hope this was okay, and we'll continue the discussion with encoder decoder network. And I think right now people don't use that anymore. People mainly now incorporate that with attention, and I was looking into that. And let me just post this again. TensorFlow's tutorials is always good, and they explain and implement everything. So you might want to look into that as well for encoder decoder network. So, all right. On that note, thank you everyone again, and have a good night.